It's easy using a two-dimensional photograph to determine if one side is higher than the other from a front or back view, or if a body part is more in front or behind another part from a side view. But it's virtually impossible to determine the amount of head or torso rotation along the up and down axis. Until now. First, let's watch a little refresher on the three-dimensional Cartesian coordinate system.
In this lecture, we will construct a three-dimensional Cartesian coordinate system, which will allow us to display ordered triples of real numbers as points in three-dimensional space. The set of real numbers R can be thought of as corresponding to a continuum of points in one-dimensional space. It is this space which is represented by the number line. Each real number corresponds to a unique point in this one-dimensional space. We then created a two-dimensional Cartesian coordinate system by taking the Cartesian product of the set of real numbers with itself to form an infinite set of ordered pairs called R squared, or more commonly R2. R2 corresponds to a continuum of points in the two-dimensional space represented by the Cartesian plane, and each ordered pair of real numbers corresponds to a unique point in this two-dimensional space. However, we are not limited to forming Cartesian products of only two sets of real numbers. We can also form the Cartesian product of three sets to form the set R3. Just as the set R2 consists of ordered pairs whose elements can be any two real numbers, the set R3 consists of ordered triples whose elements can be any three real numbers. And just as the two-dimensional Cartesian plane was built from two number lines oriented perpendicular to each other, three-dimensional Cartesian space can be created by taking three number lines and orienting all three perpendicular to each other. These three axes are typically labeled X, Y, and Z, with the positive X-axis pointing out of the page, the positive Y-axis pointing to the right, and the positive Z-axis pointing up. Just as in two dimensions, the point where the three axes meet is called the origin. The origin corresponds to the ordered triple 0, 0, 0. The three axes can be oriented in any way, as long as all three axes are perpendicular to each other, and they conform to what is called the right-hand rule. The right-hand rule states that if you align the thumb of your right hand pointing in the positive direction of the x-axis, and your index finger pointing in the positive direction of the y-axis, then your middle finger should point in the positive direction of the z-axis. For example, we could arrange the axes so that the positive x-axis points to the right, and positive y points up. In that case, the right-hand rule tells us that positive z must point out of the page. Or we could orient the axes with positive x pointing up, positive y pointing out of the page, and positive z pointing to the right. However, the typical orientation is with positive x pointing out, positive y pointing to the right, and positive z pointing up. In three dimensions, just as in two dimensions, the infinite plane containing the x and y axes is called the xy plane. Likewise, the y and z axes create the yz plane, and the x and z axes create the xz plane. These three planes divide the Cartesian space into 8 regions called octants. The octants are numbered 1 through 8 and are typically labeled using Roman numerals. Just as the two-dimensional Cartesian coordinate system allows us to graphically display ordered pairs of real numbers as points on the Cartesian plane, three-dimensional Cartesian coordinates allow us to display ordered triples as points in Cartesian space. The elements of an ordered triple corresponding to a point are the coordinates of that point. To locate a point in this three-dimensional space, starting from the origin, we move along the x-axis a distance and direction specified by the x-coordinate. Then from that point, we move parallel to the y-axis a distance and direction specified by the y-coordinate. And finally, we move parallel to the z-axis a distance and direction specified by the z-coordinate. This determines the position of our point in Cartesian space. Another way to look at this is that the x and y coordinates locate a position on the xy plane just as in two dimensions, and the z-coordinate specifies the point's distance above or below that position on the plane. Now that we have a way to visualize ordered pairs of real numbers as points on a plane, or ordered triples as points in space, the next step will be to create sets of ordered pairs which represent relations between different types of quantities. If the quantities can be represented by real numbers, then these relationships can be visualized in two- or three-dimensional space.
Okay, now back to the original problem of accurate rotation measurements in the z-axis. How can you do it? It's just a matter of perspective. You can see in the front view that we don't have good visual clues to determine the amount of head rotation or torso rotation, but we do have that perspective in this view that's taken from behind and slightly above. From this perspective, we now have good anatomical landmarks we can use to draw lines to show us accurate measurements of rotation. So here's how you take that shot. For children, you probably won't need anything to elevate you above them, but for adults, you will need some type of step stool or a chair to stand so that you can have the camera pointing above down. This will give you the proper perspective and render an image that looks like the one in the lower left-hand corner. Now that we have the image we need, let's see how it's analyzed in Posture Pro 8. After you've captured the image, analyzing it in Posture Pro 8 is fast and straightforward. Let's bring that image in that we just captured. We have it on the screen. Now to do the axial rotation analysis, we click on the on-screen tools. And from here we have a variety of lines and angle generating lines that we can use to do this analysis. And there are a couple of different ways to do this. Let's start with the simplest, which is just using straight lines. We can select a straight line and its color by clicking on one of the line options, and then we can draw a line right through the ears. And we see that that's not level. We can select another line and draw it through the shoulders. And we see that that's not level as well. So here we have an instant visual clue that there's a head rotation and an upper torso rotation. We can also do the lines of the buttocks to see what kind of offset there may be in that area. So here we have a very fast visual clue that there are rotations in the area. There's another way to do that, and let's clear these lines. We're going to click on the horizontal line box. The second way to do the exam is to use angle generating lines, and we select one of the 4 different colored lines that we have available, and then draw a line again through the ears, and we make a click down below the line and it generates an angle. And we can select another color, draw that line through the shoulders, and again click below the line, and it will generate another angle. So we see that we have a head rotation of 7 degrees and an upper torso rotation of 12 degrees. And we can assign this exam as an axial exam, and this will show up in the list of analysis that we've done for this patient, and we can print this out on the report. So Posture Pro makes it very fast and easy to capture and measure axial distortions to add to the other posture exams that you can do.